So, hello friends. Now, third part in the lecture series of electromagnetic induction, in which I plan to do these four topics: energy conservation, relation between induced charge and change in flux, eddy current, and AC generator. Then thereafter, in fourth part, I am planning to finish EMI. So let's proceed with energy conservation. That means here we will be proving how law of conservation is relevant in electromagnetic induction. Same diagram I'm repeating from motional EMF. Here previously, while talking about motional EMF, we didn't consider forces, but now magnetic force due to straight conductor F is equal to ILB we are to consider. How? Let's see. Here induced current I in the circuit. I is equal to E by R. Here this E is induced and R is the resistance of the rod PQ. Then E is equal to BLV upon R. So this was the induced current. So as current flows through the arm PQ, it will experience a force due to the magnetic field. This F is equal to ILB and I is E by R. It implies that F is equal to B square L square V upon R. And in the diagram, we can see speed is in the leftward direction, whereas magnetic force will be in the right direction. Let's check from Fleming's left-hand rule. No, force will be also in the left direction, current into the field. So that's why. That means magnetic force is in the rightward direction on the rod. So I must specify this point. Direction of this force will be towards right, opposite to that of velocity from Fleming's left hand rule. Remember, while finding out the direction of this magnetic force, induced current was not in the picture. That's why we didn't apply Fleming's right hand rule. Instead, we had applying Fleming's left hand rule for this purpose, because this involves completely magnetic effect of current. To keep this rod moving against rightward magnetic force, equal and unlike force is needed to move this rod with constant velocity. And for this purpose, definitely power is needed. And that power thing we are to discuss over here. P is FV and F will be this B square L square V upon R. Therefore, P is B square L square V square by R. The power spent is dissipated as joules heat. That's why heading name is law of conservation of energy. The power spent is dissipated. Same power, whatever power we have put, the power spent is dissipated as joules heat and is given by I square R. And I we had BLV upon R. This is equation number 2. Therefore, from 1 and 2, the mechanical energy required to move the rod PQ is converted to electrical energy and then thermal energy. Hence, conservation of energy is completely relevant. Now, next topic, relation between induced charge and change in flux. Here we have from basic fundamental of this chapter, mod of E is equal to del phi P upon del T. That means d phi by dt. But on the other hand, it is IR. I could be written as d del Q by del T, and this can be cancelled out. Either this formula or simply it could be written, or simply Q is phi B upon R. So same formula is relevant in both the formats, in del format also and in full complete format also. And here comes eddy current has come up, in which I plan to write a lot. So what is eddy current? So there are currents induced in the bulk pieces of conductor when the amount of magnetic flux linked with the conductor changes. However, their flow patterns, eddy means swirling waves, cyclonic waves, circular waves. It is special type of induced current generated in bulk piece of conductor. Earlier, any type of induced current we had in our discussion, we had always in the form of current in the conductor, that is linear conductor. But now we'll have proper wavy current in the form of circular waves in solid bulk piece of conductor. Now we don't have current carrying wire type conductor. We have full solid. However, the flow pattern resembles swirling eddies in water. So that is why they are eddy current. Disadvantages of undesirable. Eddy currents are undesirable because they normally harm our circuits. How? Eddy currents are undesirable as they heat up the core and dissipate electrical energy in the form of heat. This way we are able to create the picture in our mind towards eddy current that it is not useful for us. But interestingly, there are some advantages. They are having some practical applications in our everyday life. We are going to discuss that small list also. But before that, methods of reducing eddy current. But after going through this paragraph, what we are thinking that since it is disadvantageous to our everyday life, so let's try to reduce these factors which are causing disadvantages. So what are the methods of reducing? Number one, holes or slits made in the plate reduces the area available for eddy currents to flow. If in the core some holes and slits are made, whatever magnitude of eddy current is generated, some currents will be passing across the holes, hence reducing. Number two, laminations of a metal are used to make a core. The laminations are separated by an insulating layer like lacquer. Lacquer is a varnish type paint type thing which obstruct induction. the plane of the laminations must be parallel to the magnetic so that they cut across eddy current paths. This reduces the strength of eddy currents and hence the loss of energy. The loss of energy as heat. E is I square R. This way, we have finished another subheading methods of reducing eddy currents, and after that, last subheading of eddy current is advantages of uses of eddy currents. Plane of the lamination must be parallel so that they cut across the eddy current paths. This reduces the strength of eddy currents and hence the loss of energy. Advantages, public uses, magnetic braking in trains, very important. Number one, in trains, strong electromagnets are situated above the rails. When activated, they produce eddy currents. They produce eddy currents which oppose the motion of the train. As there is no mechanical contact, braking is smooth. Number two, electromagnetic damping. Certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates, the eddy currents generated in the coil oppose its motion and quickly bring the coil to rest. So these are the advantages. Number three, induction furnace. They are used to produce high temperature to make alloys by melting the constituent metals. A high frequency AC is passed through a coil which surrounds the metal to be melted. The eddy currents induced in the metals produce high temperature sufficient to melt it. And number four, electric power meters. The shiny metal disc in the electric power meter rotates due to eddy currents. Electric currents are induced in the disc by magnetic fields produced by sinusoidally varying currents in a coil. So whatever electricity bill is generated through electric power meters, it is run with the help of eddy currents. And last point, in speedometer of automobiles and energy meters. And yes, last but not least, thanks for reminding me. Every day I'm talking about this in front of all the students, induction cooker. So these are very important applications in everyday life due to eddy currents only. We take these advantages. Here comes AC generator. All of us, let me remind, we are in a habit to study this topic from lower classes. And it has been said again and again, it is repeated again and again that it is a device through which mechanical energy is transformed into electrical energy. So it is the same discussion. Firstly, I would like to share one diagram. It converts mechanical energy to electrical energy and principle of working. So before discussing into principle of working, and this is the diagram. Now we'll try to understand what its construction is. Basically, let me give you some basic idea. This is the rotor, this central dotted line, which is known as the axle, and it has to be rotated mechanically. That's why from our side, in the form of input, mechanical energy is given to this system, and because of this whole arrangement, induced current is being generated in this rectangular loop, and hence electrical energy is generated. That means mechanical energy is transformed into electrical energy. But how? Let's see. This is North Pole and South Pole, strong pole pieces, which is causing strong magnetic field in this direction, and in which, because of this axial rotation, this rectangular coil is being rotated like this, and because of this kind of rotation, change in magnetic flux is happening across this coil, and hence induced current is generated, and that induced current direction is determined by following Fleming's right hand rule. How? Where my cursor is located right now, at that line, suppose magnetic field is like this, movement, because this branch is going down in the process of rotating like this, so thumb is pointing towards downward direction, and index finger is suggesting the direction of magnetic field, and then hence middle finger is suggesting the direction of induced current. That means like this, and here this is slip rings arrangement, and these two are slip rings, and this are carbon brushes, and here this way after current appearance, it will start going like this, and here across these two ends some load will be connected, through which it would be transferred in forward direction, and after this way going like this, and see one hidden line behind these slip ring arrangement, and this way ऐसे करके and this way. Meanwhile, this loop will be moving further and completing half cycle. After this half cycle, this end will come over here. Now again, Fleming's right hand rule, this time this kind of current would be reaching here. ऐसे करके would be reaching here, and this way, this time another, that means in second half cycle, current will be going this way. That means after every half time cycle, direction keep on reversing. That means polarity will keep on changing all the time, and hence it is AC current, alternating current. This type of induced current is known as alternating current, which we'll be studying further in detail mathematically in chapter alternating current. Here, this was the working in simple. Now, some mathematical analysis is left. Very few minutes of discussions is left. Firstly, few lines of construction. Magnetic field. The axis of rotation of the coil connected external circuit with the help of slip rings and brushes. Rotor shaft, which is in the diagram, axle. Strong magnetic field here is caused due to north and south pole. The axis of rotation of the coil is connected to external circuit with the help of slip rings and brushes. Slip rings, these two are slip rings, and these two are carbon brushes. Here comes working. I'll try to cut short very briefly. I'm to explain. Basically, I intend to write the expression for peak value of induced EMF. For that purpose, I need to write the expression. Few lines of mathematical discussion, the flux through the loop phi is equal to BA cos theta, where theta is omega t as S is equal to Vt. As the coil rotates theta, hence the flux through the coil changes, which sets up an induced EMF in the coil. E is equal to E naught sine omega t, be the instantaneous EMF, induced EMF in the coil. Here theta is equal to omega t, which is angular velocity of the coil. Let the coil rotate constant angular velocity omega. The flux, that means magnetic flux, at any time t would be E is minus d phi b upon dt. That means rate of change of flux with respect to time. Obviously, n would be the number of turns. E is equal to minus n d dt of dA cos omega t. E is minus n b a d dt of cos omega t. It implies that E is equal to minus n b a omega, and after differentiation of cos omega t, we have got minus also minus sine omega t, and omega is variable coefficient is being multiplied. It implies that E is equal to NBA omega sine omega t. And comparing this equation, peak value of induced EMF E naught is NBA omega. Since value of sine function varies between +1 and -1, the polarity of the EMF also varies. Hence, direction of current also varies periodically with time. Therefore, current is called alternating current. Previously, just few minutes back, we had a discussion. From that discussion, we could learn through the instrument, through the device, how current is alternating. But now here from this paragraph, we are able to understand, convince ourselves mathematically how the current is changing its polarity between the sine function from +1 to -1, or -1 to +1, and so on, so on. Hence, the current is alternating. This was the sine function, and already we had been knowing from long time that sine function and cos function both lies between +1 and -1. Lastly, I'm to include one more diagram, and lastly we could see in this diagram also, this was initial position of that rectangular coil. Then 90-degree means quarter rotation. After this, plane completely is in horizontal position. Then in the process of rotating, now half cycle it is done. Then 3/4 and then 4/4. And one more thing, here wherever I have used theta, theta is the angle between B vector and area vector. So now I guess nothing is left, and this way I have completed third part of the electromagnetic induction. So I hope you must have enjoyed this whole presentation and lecture. Now you keep enjoy our physics, and bye. See you. Take care until next video.